All right, so please, I hope my screen is being shared. Hello, please, is my screen being shared?
Yeah,
Yes,
Daniel.
yes.
Okay, good. So, as I was talking about the measuring, checking the means, the differences in means. So, apparently, we are using the new cases and the new recovered. Okay, though they do not depict what we are trying to show back then, because they do not take that kind of a before and after kind of treatment or kind of of experiment. Okay, but however, we are using it in this example to show. So I said that when you use the t-test underscore rel, you get the t statistic value and then the p value. So the t statistic value, yes. So the t statistic value actually tells you uh, the difference between the means of the new cases and then new recorded, because we know that for t-test, that is what it does, comparing the means of data. And then the p-value also gives you the probability at which that particular difference, which is the t-stat, is not purely random. So we compare this one to the significance level, which is the alpha over here, to figure out or to know whether the differences between the two columns of our data are not just by random, but they are actually true uh, differences. So we format it in order to print the mean and then the statistic value and then the main values of the columns that we have. Now, under this place, we are just looking for the condition, which we know already. What is our condition? We say that reject the null hypothesis, that is new cases and new recoveries differ significantly, country by country, if the p-value is less than alpha, else fail to reject. So what we are trying to say is that by what means do we say or do we tell that the t-statistic value obtained from this particular t-test per t-test that we've run, how is it that that's different? It's not purely by random. However, it is a true or significant difference. So we just use the benchmark over here, or this condition over here. So if p-value, where the p-value is what we obtain from this particular expression, if it is less than our alpha, which is 0.05, then we will fail to reject the null hypothesis. Okay, all right. So let's make progress. So if the p-value is less than,
Daniel,
yes,
Daniel,
yes,
please, what does the rel mean? I don't understand.
this real, you mean this one?
Yes, yes.
Okay, so you know that I was initially saying that for this particular petty test, it is done perform on the same object. Okay, so this is just a function that was created to implement the calculation. Okay, okay, so the one who implemented it called it t-test rel. So the is just a name, but it's just to tell you that like it's a t-test on two related samples. Okay, so as I hover over it, I can see that you see that there is, it tells you that it is a function. Okay, so you have the depth t-test rel, and then it takes some number of parameters. Okay, so b, a, b, so those are what we provided over here. These ones are default, so we take the default. unless maybe it is a special case where we have to modify any of the parameters. So it is just the name of the function that actually helps you to run the per t-test on two columns of your data, or two um, data that you took on your experimental subject before and after. Please, I hope that answers your question.
Yes, thank you.
You're welcome. So that is that. So here we just look out for the condition. If the p-value that will be obtained as this function calculates our t-test and then the p-value, that's p-value. If it is less than alpha, then we will reject the null hypothesis. If not, we will fail to um, rejected null hypothesis. And in this case, the null hypothesis states that the new cases, or the after and then the before data differ significantly. Okay, so we want to see whether that particular statement is true, or that particular hypothesis is true. So these tests, that's why we call them hypothesis tests, because we use it to either accept or fail to accept, or either reject or fail to reject a hypothesis. And then this is the procedure. Okay, so let me just run it for us to see the results. All right, so we have the mean and then mean new recovered. So these are the two means of the two columns that we have. The mean difference is 289. The t statistic, which is the differences in the mean. Okay, the size of the differences in the mean is 1.5, 1.566. And then our question is that is this difference, this is the size of the difference between the mean actually by random, or they are true? So we calculate, the function calculates for the p-value, okay, and then that p-value, when it is being given, we compare it to our significance level in order to determine whether we are to reject or accept our null hypothesis, which states that the new cases and the recovered cases differ significantly. But in this case, they do not differ significantly. So though you can see that when you compare the means by I, we see that they are 1,229, sorry, 223 and then 933. Very vast difference. But however, when you do the t-test, you realize that the difference is not that much. All right, so in experiments, sometimes you can have different values. However, unless you have run a t-test on it, you cannot say that the differences that you are having between in your experiments, or you are having between different samples are significant. So in an example could be like maybe in the case of nutrition, let's say food products, or let's say okay, nutrition. So you develop a product and you are testing the effect of the product on, let's say, on the glycemic index of some people, maybe healthy people. Okay, so before you took their glycemic index, and then you check their the glycemic index to know the level of glucose in their blood, and then after taking it, you checked it. Okay, so based on checking, maybe before you checked and then after taking your product or your intervention um, um, material, you check the blood glucose again. Now, after all, you see that you have data. So maybe you check it at some time interval for the two individuals. When you are done, you will see some differences. But for you to know that the differences between the before they took the intervention and after they took, is it something significant? Is it something substantial? That does it really count? Okay, so it helps you to make informed decision as to when it comes to research, because if people take the bread, or maybe people take the product, or maybe you found something, some mixture of some organic foods, and you think that that reduces the blood sugar, and after the people took that bread, and I mean that product, and then the differences are not significant, then there is no need for you to say that maybe your product actually reduces the blood sugar, because the differences, the reduction in the sugar level, blood sugar level is not significant. Okay, all right. So we don't look at numbers to say that this thing is wide different. No, in statistics, we use the t-test to handle all these. So apparently, you realize that the p-value tells whether the difference is statistically detectable. I mean, is it statistically significant? But however, it does not give us any knowledge of how, I mean, the significance, how significant it is. Okay, so the t-test will tell you that, okay, so because maybe the p-value is less than the significance level, which is 0.05, or is greater than, okay, it is significant. I mean, the differences are significant, but it does not tell you how significant it is. So if you're telling me it is significant, by what parameter, by what factor is it significant? If it is not, by what factor? So the Cohen's d actually helps you to calculate for uh, the, the the size. How big is it? So how do we implement? So we have the Cohen's d um, equation to be there. So this is actually the equation that solves the Cohen's d, which gives you the size of the significance. To implement this, we are going to write a function in order to make the work a bit simpler. How are we going to do that? So in this case, our function will be called Cohen's underscore d. And in this case, it is taking two parameters. So parameter one, parameter two. The first parameter is the sample one, which is the one column. And then the second parameter is sample two, which is the second column. We assign n1, n2 to the length of sample 1 and then the length of sample 2, and then the var1 and var2 to the variance of the sample and then the variance of the sample 2. Now, once we are done, we are going to calculate for the pooled standard deviation. So the pooled standard deviation, this is the equation that actually solves it. So you can see that in this case, we are implementing the numpy, the square root. So why is this so? Because I've told you earlier that NumPy is used for numerical computation, that because it's very extremely fast when it comes to numerical calculations or numerical computation. So for us to implement these equations um, effectively or efficiently, we use the np.square root. So if I am to show you the formula, this formula in its notational form in Google Chrome, you realize that there is a square root and then we have the length, so that's n1 minus 1, which is the length of the first sample minus 1. So you see it in that particular mathematical notation. However, the implementation has to be different because we cannot use those mathematical notations here. So this is how we do. So this puts all the things here under the square root over here. So once the pooled standard deviation is being calculated, which is here, all that we need is to subtract the mean of the first sample from the mean of the second sample and divide by the pooled standard deviation, which has been calculated. So here we are saying that return, and in this case, return the sample 1 dot mean, as we can see here, and then the sample 2 dot mean divided by the pooled standard deviation, which we have calculated from the number of samples in both samples and then their variance. So once we are done, we can call the Cohen's function. So d equals to Cohen's d. So we are providing our sample. So our sample one is Europe devs and then American devs. Okay. All right. So in this case, we are assigning d to this particular function with 8 arguments. So what d will inherit is the value that will be produced after the calculation or the compute after the computation of this particular equation. So once we are done, we are going to make a decision using our conditional statement. What does it say? It says that if absolute, so the ABS is an absolute, and we know what absolute means in mathematics. So when you have absolute of any value, even if it is negative, it becomes positive. And if it is positive, it's the same number. So absolute one or the other makes all values positive numbers without any negative. So if the absolute value of the d, which is the value that will come out when this particular equation is being calculated, if the absolute value of that d is less than 0.2, then we say that this, the size of the significance, so we are saying that it's significantly different. So the size of that significantly different is negligible. However, if it is 0.5, we say it is small. And then if it is less than 0.8, we say it's medium. Else, if all these conditions are not met, we say that the size is large. So here, let's try to see what will be the outcome. So here we calculated the Cohen's d Europe versus American death rate, and that is going to give us 0.335. And then the effect size is small. So though the differences between the death rate in Europe and America is statistically significant, that significance is small. So you see that now we've topped it up, making it more meaningful. At first we were saying that it is statistically significant, but now we can see that the significance is actually small. So the ones that the statistically significant results with a small effect size is common in large samples and is well reported alongside the p-value. Okay, so in this case, that is the conclusion that we can come up with after running the Cohen's function on the columns that we've calculated. They are we are trying to find their correlation. Sorry, we are trying to find the differences in their means, how different they are from one another. Okay, so that is that for Cohen's. Up to this stage, please, if you have any question, you can let me know. If not, so we'll.
Daniel, please can you explain the coherence again? At a point, I wasn't getting it.
So the Cohen's tells you how big or small is your significance. How big or small is that significantly different mean or different value between the columns that you are comparing. So initially we were trying to say that if you have two columns and you compare those two columns, you can try to find you can find the differences in their mean. And then by that you can say that the differences in their mean is significantly different. And then the question is, okay, you are saying that it's significantly different. What is the size of that difference? So that is what the Cohen's does. And then here it uses this particular equation to calculate. To implement that calculation, this equation here, instead of manually inputting everything, we just create a function that takes your sample 1 and sample 2, which represents your columns, and then calculate the length of them and then their variance, as well as their means to calculate for the Cohen's d. So once the Cohen's d is being calculated over here, then we can compare it to all these thresholds to tell whether the differences in their mean is to tell the size of the differences in their mean, whether the statistically significant difference is small or big or negligible. Do you get it now?
Yes, I do.
Okay. Please, any other question? Okay. If there is none, then we make progress. All right. So we move on to one way and over. Okay, so you can see that previously all that we have been doing is to compare exactly two groups. Okay, so what if we have more than two groups and then we want to compare? Then we need to use the ANOVA. So the ANOVA tests all groups at once with a single p-value. So let's move on. So let me read the intuition. So ANOVA asks, is the variation between group means larger than the variation within each group than you would expect by chance? So he said that if regions genuinely differ, the region to region spread should dwarf the country to country noise inside each region. So basically, what the ANOVA is doing is just a way of performing the same t-test, as in figuring out the differences in the means of the data. However, in this case, it is being implemented on multiple columns or multiple groups other than exactly two groups for the previous t-test that we've been able to run. So zoom into the code to see its implementation. All right, so here we are seeing the regions. So this is the WHO regions. We are giving it regions, and in this case, we are not just returning the all the columns in the all the values in the WHO region column. However, we are returning only the unique values. So only the unique values will be returned. In this case, you see each of the continents. And then we say that groups equals to df. Okay, so let's look at this code implementation. So it's actually a list, right? So it's kind of a list comprehension. So all this code is saying that df here, okay, so this particular code is saying that the WHO region equals to region, whereby the regions equals to region. So whereby the regions over here assigned to each of the unique region. So we are saying that df equals to WHO regions. Okay, so for these ones, we are selecting the death per 100 cases, I mean the death rate for each of the regions in region. So it's more of like saying that for region in regions, DFWHO equals, sorry, DFWHO region equals to region. Okay, all right, so when you're done, then you subset. Okay, all right, so when you do this, it groups them in accordance to their death rates. And then since we have a list here, we can actually perform something wonderful. So if you recall the zip function, which bundles two lists together. So in this case, we say that for region, comma, group in zip, comma, and zip, and then we are providing the regions over here and as well as the groups over here. So what we are going to print is the length of the group, each group, and then the mean value of each group, and then the standard deviation. These are the values that we will use to perform ANOVA, one-way ANOVA. So let me run it so that we get to see how the data presentation will look like. So here you have the Eastern Mediterranean, and then the number of countries is 22, or the number of death cases there is 22. I mean, death cases that belongs to the Eastern Mediterranean countries. So in fact, the number of Eastern Mediterranean countries is 22. And then the mean, this mean is calculated on the death per 100 cases, as in the death rate. And so the standard deviation just cuts across all the other uh, continents or regions that were included in the data. So once we are done and sorry, we've had this particular data, we can actually, wait, we can actually use it to calculate for our one-way ANOVA. And so, and this is the implementation. So the F statistic and then the P value, it equals to start dot F underscore one way. And then we say that asterisk groups. So the asterisk groups will select all the data in the groups. Okay. So now once we are done, then we can print the S statistic and then also the P value. Now we create a condition to help us decide whether we are supposed to reject the null hypothesis or fail to reject the null hypothesis. And the conditions has been same since previous. So if the p-value is less than alpha, then we will reject. If it is not, so if it is greater than or equal to alpha, then you will fail to reject. Now, what is the null hypothesis? The null hypothesis is that at least one WHO region has a different mean death rate. That is the null hypothesis that we are testing. So let's run it and see what will be the outcome. So when we run, the S statistic is 3.318, and then the p-value is 0.5 less than 0.05, and if it is less than, then we are going to reject the null hypothesis, saying that the hypothesis that at least one WHO region has a different mean death rate is false. So not at least one WHO region has a different mean rate. Okay, no significant difference across the region. So it means that the mean death mean rate across all the regions, there is in this case we are rejecting. So it means that at least one WHO region has a different mean. So that means that the differences that there is a difference in the means. Okay, there is a differences in the means of all the regions that we've checked. So here we have 6 regions. So there is differences in their means. Okay, at least one, at least one. All right, so we can visualize all the 6 groups using a box plot. Okay, so the box plot implementation is just the data frame that we have, the box plot. And then the columns that we are using is the death per 100 cases. And then the groupings is by WHO region. And then we assign our acts to acts, and then that is the. So in this case, we have the box plots, which also to compare the differences in the mean or the median of each of the WHO regions. So by just visualizing and looking through the box plot that we have for each of the data sets, we will realize that the median of each of the WHO region is different. Okay, and in this case, significantly different. So we are moving on to the 2-case HSD, which stands for the 2-case honestly significant difference. So we realize that ANOVA gives an overall probability p-value, and then that p-value tells whether the difference in the means of the groups that we are comparing, whether it's by chance or it is actually something significant. So initially, when you run the t-test, I mean the previous t-test without the ANOVA, you will realize that when you try to repeat it over for multiple columns, you are going to increase the false positive rate. The false positive rate is a condition whereby um, uh, the outcome of a particular t-test is actually is actually a false, like it's a false, but it's being considered as positive. So though the significance, there will be no significance, but based on running the t-test on multiple columns or multiple groups, we are going to have an increase of that particular false positive rate. And so as a result of that, we implemented um, the the ANOVA in order to calculate for the overall. However, the two-case HSD also helps us to actually control the overall false positive rate. So let's try to see how that also works by just running the code. So in this case, if we want to use the two-case HSD, we need to import it. We need to import it from the start model, the start, the multi-comp imports the pairwise two-key test. So all these are parts that we can find this particular 2K HSD function. Okay, so once we are done, we assign a variable to the pairwise 2K HSD, and then we provide the data that we want to work on, and then the WHO region, because that is the groups that we want to, that is how we want to group the data. So we are grouping the death rate by the WHO region, and then the alpha, which is the significance value or level, we set it to 0.5, and then we print the 2K, and that is going to give us the 2K statistically significant difference. So let me run it and let's see. So this is the output of the 2K function, I mean pairwise function. And then how do we interpret this particular data? It says that if the reject, under this reject column, if the reject value is true, it marks that the pairs of region whose death rate, and it marks the pairs of region whose death rate differ significantly. So in this case, in two-case test, you see that initially I was saying that for t-test, we just run it 1 to 1 to, like only exactly 2 columns. But if you want to do it multiple times, that is when the false positives increases. That is, items will appear to be significantly different or significantly different when they are not. So as a result of that, we use the two-case significant difference to handle that. And so how do we get to know that the differences are significant or not? So here the reject gives a summary of that. So we can just tell whether the differences between two regions or pairs of region are significantly different or differ significantly. So Africa and Americans, their death rates do not differ significantly because their reject status is false, and so they are not. So we can say that over here it is only Europe and Western Pacific whose death rates are significantly different. So that is what the 2K does. And this one, it handles it without increasing the false positive rate. Alright, so basically that is that. Any question on what you've done so far? Please, is there any question? No question, I guess. Okay. Right, so let's make progress. So we also have the chi-square um, test of independence. Okay, so the chi-square is used to handle categorical variables. So when you talk of categorical variables, we are talking about non-numeric variables in our data set, which comes in categories. Categories, we can have the ordinal, nominal, and all those stuff. So in this case, we use the chi-square test to check whether two categorical columns are related or independent or not related. Okay, all right. So um, it tries to find a question like, I mean, it tries to answer questions like, is treatment outcome related to treatment group? Okay, and then it's maybe voting preference related to region. Okay, so maybe there is a vote, or even when it comes to, let's say, biology, um, let's say molecular biology, it can be like gene expression. So is gene expression related to a particular state of the organism? Okay, or is it related to, so let's say, let me just use insulin and then glucose level. We know that we've learned that as glucose increases, insulin has to also increase in order to increase the the metabolism of glucose to prevent its accumulation in blood, because excess of glucose in the blood is toxic. So in this case, we would like to figure out whether maybe those two conditions are related. And in this case, we use a chi-test, and it does not use numerical values. However, it uses categorical values. Let's see the implementation over here. So here we are going to build a categorical column called severity. So we are adding a new column to it. And in this column, we are going to use some conditions. So we say that NP, which is numpy, where DF confirmed is greater than 500,000, label is critical, 100,000 high, and then where is greater than 10, sorry, this one's 10,000 low, else all the rest should be tagged low. So you see that a new column will be created in our data frame, whereby it checks for the confirmed data and looks for these of the conditions, and where they meet is they were either critical or high, medium, or low will be assigned. In this case, after we are done, we create a cross tab. So the cross tab, let me run the code to explain the cross tab for you. All right, so in this case, you see that when we run our code, let me just also add a df sense now. The df will be working. Let me say df. Okay, so let me choose two columns. So in the two columns, I want to choose um, WHO region. Okay, and then also the severity. Okay. Okay, so let me just use dot here to print the first file. Let me just thread. Good. So you see that in our what we are done, what do we do? That what the cross tab, the pd.cross tab does is that it creates out of these, okay, out of these values in this under the severity column, it makes all the unique values as columns. All right, so you have the critical, high, low, and the medium. And then for each of them under the WHO region, how many countries were under the critical column or had that critical threshold over here? So here it returns 0, and it will do same for all of them. So that is what the cross tab does. So the cross tab is saying that what we are going to do is that make the WHO region the rows, and then make the DF severity the columns. So that's what the cross tab is doing. So once you invert it like that, what will happen is that the proportion of each of these regions to the to as to whether they are critical or high will be given. Okay, so once we are done, we can make progress. So we are done, and then now we have our contingency table. Okay, all right. So what can we do with the contingency table? We are going to calculate the chi-square. So we have the chi-square, we have the p-value, we have the degree of freedom, and then we have the expected value. So in this case, we use the stat.chi-square contingency, and then we provide the contingency table that we've created as an argument. And it is out of that table that Python and the SciPy package of Python is going to handle the is going to provide the chi-square and then the probability value, or the probability that the data or the two I mean the probability that the regions are related or not. So in this case, we create a condition to either reject or fail to reject the null hypothesis. So let's run it and see what happens. So the chi-square statistic, which is the relatability or differences in the data, is 35.90. Degrees of freedom is 50. And then the p-value is 0.08. So let's look at the condition. Since this p-value is way less than 0.05, then it means that we are going to reject the null hypothesis, which says that severity and WHO region are not independent. That is, they are not related. So the chi-square helps us to figure out whether there is a relationship between one column and the other. So we are saying that is the severity which was calculated or gotten out of the number of confirmed cases, is it related to the WHO region? As to is there a difference? Does the region where the people are influences the severity of the confirmed cases? That is the question that we are trying to ask. And to make that possible, we use the chi-square to calculate that. And then the outcome here from this particular um, data that we have is that the severity and WHO region are not independent. So if they are not independent, then it means that they are related with each other. As to, it means that based on where you are, then I mean the severity of the confirmed cases as to, are there more confirmed cases? Is the confirmed cases status high or low? Is it severe, or it is dependent on region? So by so doing, you can say that okay, so COVID came. However, based on the data that we have, we can say that the number of confirmed cases or the severity of the disease, which is measured by the confirmed cases, is related or dependent on the region where the person is coming from. Please, I hope the intuition is clear. Please, is it? Please come again, Grace. So I was saying that the question that we are trying to ask is that
Daniel, please
we've
go over.
calculated the severity of the COVID-19 using the number of
Please
confirmed
go
cases
over.
per each country. And then we've grouped the number of confirmed cases per each country into continents, which is the WHO regions. So I'm calling them continent, though they are not the continent that we have. But according to WHO region, those may be considered as continent. So we are trying to figure out that does the severity of the COVID-19 based on the number of confirmed cases related or dependent on the region where the people are coming from, or the region on the surface of the earth, or the region of the planet. So that's the question that we want to ask. So in order to do that, that is what we start by implementing this particular calculation. or logic in order to segregate critical regions, high regions, low regions, and the medium regions. And once we've been able to perform that segregation, what we do is that we make a crosstab. The crosstab is just a tabular data or a tabulation of the severity against the WHO region. And this is how it looks like. And I was explaining that, see that we have the WHO region in the rows section, and then now the severity is on the column section. And then we are providing the number of each of the severity categorical values based on the WHO rate. So Africa, how many African countries had critical cases? 0, high 1, low 40, medium 7, Americans 2, and so on and so forth. Please, do you get it? So once we have this data becomes the data that we will use to calculate the chi-square, which will tell us whether the severity and the WHO region are related or they are not. So by calculating the chi-square, we use this particular Python expression, and we provide a contingency table that we've created over here as an argument in the chi-square contingency function from the stats model. Now, once we had the value, we just compare the p-value, the p-value, which tells us whether that particular relatability is by random or it is a significant value. So once we compare, the first condition is that if the p-value that we get from here is less than the significance level, okay, then we are going to say that the null hypothesis is being rejected because, and the null hypothesis says that severity and WHO origin are not independent. That is, they are not related. Okay, all right. And then if the p-value is greater than the alpha, greater than or equal to the alpha, we will fail to reject the null hypothesis and say that no significant association detected. That means that the relationship between the categorical value, well, I mean the WHO region, which is categorical value, and then the severity, which is also categorical value, there is no association. And that even if there is an association, that association is not statistically significant. So the first one said that it is statistically significant, and the second one says that it is not. But in this case, it is far less than the 0.05. So we say that the differences, okay, or the relationship between the severity and then the WHO rating are statistically significant. That is, they are related, and then that's related as in the maybe based on the WHO region would determine the number or the severity of the COVID-19. So we are saying that that particular relationship is statistically significant. Please, I hope you get it. Okay, you're welcome. All right, so that is that. So yeah, it's just a bit um, something that we can. So
Yes,
in this
I
case,
do.
this is
Thank you.
our that's cross tabulation that we did. But you can see that when we were running um, the statistic, I mean the chi-square contingency, we got an expected value. Okay, so in this case, we can also print out that expected value over here. And then this is how we can actually output that expected value. So we just put it in a data frame. Okay. Okay, so once we do that, the expected value will be calculated for us. Okay, so it's just an application of this expected value. So this expected value. Okay. So once we are done, we say that um, so the common rule of thumb is that the chi-square test is unreliable when more than 20% of the expected cell counts fall below 5. So it is therefore advisable that we glance at the expected counts table before trusting the p-value. So we are saying that the p-value that is here, before we can actually um, accept it, we need to also print the expected count. Okay, we need to also print the expected count value. Okay, okay. So this is the expected count if the two variables are independent, if they are not dependent on each other. Okay. Sorry, if they were independent, yeah. So that is, it means that if they are not dependent. So these are the values that we have. However, to the comparison that you need to make is a bit technical, and I just brought it that there is something that you can do this, but it goes beyond the scope of what we are doing. So I'm not going to give the intuition behind the reading, but however, you can also bear it in mind that sometimes when you get a p-value, you can also calculate for the, or you can also take a look at the expected count in order to see whether your p-value that you had is something that is should be accepted or not. So as part of learning process, you can also make it your goal to also understand it when you have the notebook and then you're going through to in order to read it, and then um, explain it yourself. Okay. All right. All right. So the last thing that we, yes.
So Daniel, what do we
Yeah,
have
so
to
that is
look
what I'm
out
saying
for
that
from the expected
it's
table? Like, how do
how
we
to read it
compare it to
is beyond the scope of
the
what
p
we are learning
values that
today.
the p
Okay,
value
I
that we
mean,
had?
so I'm
I don't
giving
get
it
it.
as an exercise for you to also go and then try your hands on. So you read around it to figure out how to read and how to compare the observed count, which is your data that you get. I mean, your contingent table that you get after creating your cluster of your two categorical columns. So as you are done, you are the expected value that to be calculated will be applied to the column here, these values over here. So this is the theoretical expected value, and this is the actual value. So there is a way that you can compare it. However, I'm not going to show you that. So I'm saying that do go and do that by yourself. Please, I hope you get it. Okay. So we're moving on to correlation. So correlation, um, I hope we've met this thing. So it tells us how,
All right.
um, I mean, the relationship between two values. How do two values move together? So if you recall, when we were doing the math plotting, we came across um we came across some scatter plot. Okay, so when you have a scatter plot, you can either have a linear regression line through your data to also see that, oh, this thing is maybe correlated or something, or even by just visually looking at your data, you can realize that maybe as you moved along the x-axis away from zero, and then as you move on the y-axis away from zero, you can see that the data is either moving upward or it is descending. So by just using that visual analysis, you can tell whether there is a correlation. But however, if you get a value to confirm that correlation, how to get a correlation, not just by visually saying, to see it is positively correlated by what value. Okay, so that gives us the opportunity to also um, use the correlation. So in this case, we are going to use, we have some different types of correlations. So we have the Pearson and then the Spearman. Okay, so this returns a correlation and then the p-value. Okay, all right. So always the p-value tells you whether the value that you've had as in the correlation is by chance or it is statistically significant. So in this case, we want to find the correlation between the confirmed cases and this. So do they move together or they do not? So we are using the Pearsons. Okay. So um, in the Pearsons, one thing that we can note about it is that it assumes that the relationship is linear. So the relationship between your data set, the two columns are linear, and then the data is roughly normal. So we've talked about normality already, so I don't have to explain that. So once you use the function, the Pearson function on the two columns that you want to work with, you're going to get the R value, which tells you about your correlation, and then the p-value, the probability. So we can have a threshold over here to either reject or to either say that the correlation is statistically significant or not. And always the p-value should be less than alpha in order to say that it is statistically significant. So let's run this particular code and see the outcome. So the Pearson correlation value was 0.935, and therefore a positive correlation because there is no negative value over here. And then the p-value is 0.00000. Okay, so it means that the confirmed cases and then the test cases, they are positively correlated because 0.935 is almost close to 1. Okay, and then the perfect correlation is 1. Okay, so this one is almost close to 1. And so there is a positive correlation, and then the correlation is so statistically significant in such a way that the p-value is 0.000. Okay, right. So we can do some visualizations with the scatter plots. Let's just look at that and then let's see. All right, so with this, you can see that we have our this here, then our confirmed cases. So as we move from zero away, as we move away from zero for the confirmed cases, then we move away from zero from the dev cases. We see that as we are moving, as confirmed cases increases, the dev cases also increases. This is how we can say this for ourselves. Please, can we see this? Okay. All right. All right. So we are saying that that's for the Pearson correlation. And
Yes,
then we
we
say that
can.
it assumes linear relationship, and then that the relationship between the data is linear. However, it is sensitive to outliers. That is to say that when there is an outlier, like these values, they influence the correlation. Okay, though it gives you a fair knowledge of how correlated they are, provided they are linear. There are times that the differences, I mean, the two data will not assume a linear kind of correlation. Okay. So in this case, um, the Spearman's rank correlation helps um, to measure whether two columns move together in rank. And in this case, it does not care about the relationship. Okay, it only cares about the consistency in increasing or decreasing. So do the data increase together or do they decrease together? So the Spearman puts into considers the linear relationship between, and the values are, are, are very crucial. But in this case, we are just using ranking. Okay, we are ranking the 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 two columns that we want to find the correlation between. So let me run the Spearman and then let's see how that is going to be. So we see that the Spearman also gives 0.939 compared to 0.935. So they are a bit close, and then they all had a p-value of 0.0000. So so that is that for the Spearman correlation. So both of them calculates for the correlation, but with two things, like with different things in mind. Okay, okay, I think we have a plot source issue. So this is what we call the correlation matrix. So how was the implementation? So numerical columns. So we select all the columns that has numerical values. And then it's the call matrix equals df calls.com method. So we are using the spearman. Then we are rounding it to two decimal places. So we are running the spearman correlation on the df column. So df columns, numeric columns, will select all these columns. And for all these columns, we are running the correlation, spearman correlation of them. And we are rounding the values to two decimal places. Once we are done, we set our args and then we are using the seaborn. So this is where the seaborn was implemented. So seaborn, and then we say that heat map, and then we provide the correlation matrix as our argument. Okay, then we give the annotation, and then the C map, we choose the color, and then center, then we set the axis to that axis over here. All these ones we know already. So there's it. So how do you interpret this data? So this data shows you the correlation. Okay, uh, so start from -4 to 1. So as it is approaching 1, then the color becomes this one. I don't know, but it looks for me wine kind of. I don't know whether it is wine or something. And then we have the is it sea blue or something. So in this case, you can see that um, the correlation between confirmed cases. I mean, when you look at it, you see that there is one throughout, meaning that the correlation between two same columns, as in confirmed and then confirmed, is always one. Def and def is always one, so that's why we have the 1 1 1 throughout. But confirmed and then def is 0.94. Confirmed and then recovered. So that's the correlation. So it gives that. So there is a negative correlation between the confirmed cases and then also the recovered, the rate of recovery. So it's negative 0.19. So this just give you a total like wonderful statistical summary of the correlation instead of doing it one by one. This code implementation, just some few lines of code. The most I don't know what is so new here. Okay, but I can see that there's nothing new here. Just simple code. So that gives you this wonderful chart. Yeah. And I guess it's very beautiful. This one, once you put it on your LinkedIn profile, it's going to speak a lot about you that you know. All right, so we are done with the parametric testing. So um, yeah, so so in that case, we assume that there is a normality. Okay, usually we are working in topology and normality. That's why initially we were trying to figure out whether the data that we have assumes a normal assumes a normality, as in the distribution. So when they are not normally distributed, then we have alternative um, alternative statistical tests that we can perform. So for independent t-test, that is when the data is normal. But if it is not normal, we use the Mann-Whitney U-test. One way or another, we use the Puskar-Wallis test. And then the pair t-test, we use the Wilcoxon. Wilcoxon sign rank test. Okay, sign rank test. Yeah. So that is that. So we have that. And so the implementation is almost the same, just that in this case, the data does not assume a normality or a normal distribution. So before you always perform any statistical analysis or t-test and all those stuff, you first have to check for the normality of the data. Very crucial. You need to interpret it. You need to understand, is this data normal? So once you do the the histogram to check for the normality. You can also use the statistical testing to test whether it is normal, as we saw earlier. And then once you have done that and you get to know it is normal, you can go by the parametric test. If it is not normal, I mean, if it does not assume normal distribution, then use the non-parametric alternatives, and they are going to work beautifully for you. So here you see that you have the U test, that is the Whitney, Whitney U, okay, U test, and then so that's the U stat, then the P value. So the statistically and the stats value, that's in the differences in the mean. Then we are comparing Europe death and then American deaths, and then we are saying the alternative equals to two-sided, right? So because we are doing it's an alternative for the independent t test, okay, so two-sided. Once we do that, we have the same conditions that we checked for, and it's going to be a similar thing with the same explanation as I've given. And then the Kruskal-Wallis tool is an alternative of ANOVA when the data is not normally distributed. The same thing. All right. Okay. So basically, this is just a very quick summary of everything. So let me just take us through as we wrap up. So, that choosing the right test, a quick reference guide. So I just provided this to help you. This one you can refer to it anytime, anywhere. So it said that does my sample mean differ from a known value? Then we are going to do one sample t-test, and then you need only one numeric sample. So in this case, it's a numeric column. Do two independent groups have different means? Numeric, okay. They should be normalized. When I say normalized, I mean that the distribution should be normal. Then we are using the independent test. So do two independent groups differ without assuming normality? So numeric and the data is skewed. So that's why when you draw the histogram, you do the histogram plot. Okay, you realize that the data is skewed either to the left or to the right. So with that one, there is no normality. Use a Whitney U test, which we saw earlier. Do two paired or matched measurements differ? Okay, numeric link pairs, paired t-test. Do three or more independent groups have different means? Numeric. When it is normal, you use ANOVA. When it is skewed, you use Kruskal-Wallis. Wallis, yeah. And then um, are two categorical variables related? Use the chi-square. How strong do two numeric variables work together? Use the Pearson or the Spearman correlation. So basically, here comes the end of our um, our introduction to statistical analysis. Please, if you have any question, you can kindly go ahead and then